Welcome all to our next video about prototyping our new lithium batteries for our Hybrid Performance Cruising Catamaran that we are building and then sailing around the world.
But before we get started, we got some bad news.
Our kit is ready, as is our rigging, sails, etc., all sitting in a shipping container in South Africa. Unfortunately, for the first time ever, Schionning Designs is having trouble with all the major shipping lines. They are no longer willing to accept our container if it includes epoxy, which they now consider a hazardous material.
This is delaying our shipment, and that is costing us money since we've already booked our build site, and payments for that start in January. This could delay our shipment as far as March or worse. We're still trying to figure out what to do. We'll explain our current plan by the end of the video.
We always try to look on the bright side of things. We won't waste the time while waiting for the shipping container to arrive. We'll get to work on other parts of the boat we can work on, like the hybrid system batteries and some other equipment we can build. Since we are a hybrid propulsion boat, we need a lot of battery power. In fact, 690 amp hours of lithium batteries, 460 amp hours for the catamaran, and 230 amp hours for Traveler are tender. That many marine lithium batteries cost a pretty penny, as we will show you in a moment. But we've come up with a solution.
We're going to show you how we are prototyping a new lithium battery that saves us a lot of money, weighs less, and has all kinds of safety features built into the battery.
So, come join us, and we'll explain all about our lithium battery options, especially the prototypes we are designing. Okay, let's get started. Some of our viewers have asked us to talk about the lithium batteries that we plan to use on our performance catamaran. So, let's talk about the batteries we will use to sail SV Lynx. The safety of our crew must always come first, and a fire on a boat is the worst nightmare. So, when seeking to add lithium batteries to SV Lynx, the first thing we had to consider was the battery chemistry. These are the three that we researched, which are number 1, NMC, number 2, LTO, and number 3, LFP. Let's put these three chemistries into the Goldilocks and Three Bears scenario. NMC refers to nickel manganese cobalt chemistry. You all use devices that feature this chemistry. They are in your cell phones, your laptops, your tablets, etc. The reason this chemistry is used in those devices is that it's the most energy dense of the three we're going over today. Energy dense also means lighter for a given amount of energy storage. Since keeping a sailing catamaran light is critical to performance, at first glance, these seem like the batteries to use. But not so fast. Safety comes first. The issue with NMC chemistry is that it is susceptible to thermal runaway. That's a fancy term for it burns very fast and hot once it ignites. A while back, Samsung had some issues with one of their phones igniting when their NMC batteries had thermal runaway. Another famous and sad story is what happened to a dive boat in California. I've gone out on that very dive boat over 100 times back when I was an active scuba instructor. One night, while out on a dive trip, it is believed that some NMC batteries, either for cell phones or underwater cameras, ignited while charging. The entire boat went up in flames, killing 34 divers who were asleep on board. Obviously, thermal runaway of NMC batteries is no joke on a boat. In our Goldilocks metaphor, NMC chemistry for our boat batteries are too hot, so we have eliminated NMC batteries for SV Lynx. Next up is LTO chemistry, or lithium titanate oxide. This chemistry has three advantages. It is very fast to charge, can be recharged 7,000 times, and they are incredibly safe from fire. That sounds like a great combination, until you learn that they are not very energy dense, making them extremely heavy and large. So in our Goldilocks terms, that porridge is too cold. Yet, if there were no other options, we would go with LTO batteries and live with the weight, but fortunately, there is a third option. Our final contender is LFP, lithium iron phosphate. This chemistry is also called LiFePO4. These batteries are not as energy dense as NMC, yet they're better than LTO. Yet like LTO, they're very safe from thermal runaway and dangerous fires. We've seen tests by a fire department where they punctured, shorted, overcharged, and otherwise abused LiFePO4 cells, and they still couldn't catch on fire. In the end, their combination of good energy density for lighter weight, reasonable cost, and good fire safety makes them the best choice for SV Lynx. In terms of Goldilocks, LiFePO4 batteries are just right. So, now that we've decided on the chemistry we'll use, we started looking for our batteries. It turns out that China dominates all sales of prismatic LiFePO4 cells. Therefore, even if you're buying a battery assembled in the USA, pretty much all the cells were manufactured in China.
So if the cells everyone uses are all from China, what sets batteries apart?
Mainly, it's the battery management system, the wiring, and what houses these parts, plus any other features they might offer, like a heating system if the batteries will be used in places that reach below 0 temperatures. First, let's look at the two big guys in the marine industry, Relion and Battleborn. You'll see that these two battery manufacturers are used in many boats that need large lithium battery banks. A third option we have seen used is Big Battery, so we'll throw them into the mix for comparison. Now, before I get started, if you have any of these batteries, you are likely fine. They have all been used on many boats. If we were choosing between these three, and price was no object, then we'd likely go with Relion. The reason for this is that they offer a large 48-volt battery, which is what we need. Battleborn makes good batteries as well, but they only come in smaller 12-volt size, which means we would need to use something like 20 Battleborn batteries to get to just 24 kilowatt hours at 48 volts. We would also need another 10 Battleborn batteries for our tender, with all those cables, and they could not be easily moved out of the tender when we want to convert Traveler into a dinghy. That's just too many connections and battery cables to deal with, so that ruled them out for us.
Unfortunately, Relion batteries are very expensive. Recent price checks show them costing something like $1 US per watt.
If we do the math, for 24,000 watts of Relion batteries, that would be $24,000 US. And the tender batteries would run an additional $12,000 for a total cost of $37,000. Now, Battleborns are less expensive at around 89 cents per watt. And they would still have a total cost of $32,040 plus all those separate cables and cells to deal with. As for Big Battery, they are the least expensive of the three options, coming in at around 52 cents US per watt. We would need 4 of their 120 amp hour 48 volt batteries to get to the 23,040 watts for the main boat, and another 2 of their batteries for the tender. So that means we would need 6. That would cost just about 18 grand US. That's still a lot of money, though they are significantly less expensive than the first 2 options. However, we watched one couple who are on a catamaran who bought some big batteries, and they had to take them apart to add a better battery management system. So, that's a lot of extra work and cost to add on later. Even so, they would still be far less expensive than those first 2 options, even if you had to do some extra work. For us, on our performance catamaran, the issue with big batteries is weight. Those beasts weighed 210 pounds per battery, and we would have 6 of them, for a total weight of 1,260 pounds. Yikes! 30 Battleborn batteries would weigh 930 pounds, so that's a lot better, while 6 Relion batteries would weigh 990 pounds. So we were left with a choice of the larger 48-volt Relion batteries, but at a high price, or the lower weight of the Battleborn batteries, but having to deal with 30 separate cells, or the lower cost of the big batteries with their heavy weight and the needed modification. Our answer was none of the above. What I wanted was a larger 48-volt battery that weighed and cost less, with a top-notch battery management system and a case designed for the marine environment. But that seemed like we were looking for a unicorn. So unable to find what I wanted, I decided to see if I couldn't design what I needed. I mean, after all, The LiFePO4 cells I would use would be the same Chinese branded cells that everyone uses. So no difference there. I started looking into the list of parts and what I would need and what the cost would be, the weights, and then I created a 3D model of them to see the size that they would be and if I could fit them into a waterproof case. My first model was a 230 amp hour 48 volt battery, but after calculating weight, I found that they weighed a whopping 230 pounds. Still, I'd only need 3, so all total, they only weighed 690 pounds, and that's both the tender and main boat batteries combined. They were well under the weight of the lightest of the commercial batteries, which was Battleborn at 930 pounds. My issue was that lifting these individual 230-pound batteries around the boat would be backbreaking and difficult, and there was no way I could easily lift them in and out of the tender. They were also a bit large to fit into some tight storage on the main boat. So I went back to the drawing board and cut the size of my design into less than half. I created smaller, lighter, 24-volt, 230 amp hour batteries. By dropping to 24 volts, I could make them smaller and lighter. Then, just put 2 of them in series to get back to 48 volts. In this configuration, I would use 4 of them on the main catamaran and 2 in the tender. Each battery now weighed right around 100 pounds. So, all total, these weigh only 600 pounds, give or take a few pounds, since this is all on paper at this point. We'll weigh the prototypes once they're finished and report on their final finished weight. Still, I doubt we are far off the weight since we totaled all the weight of all the parts and the case that we're putting them in. So we should be within a few pounds. These batteries are a minimum of 330 pounds lighter than the other options and 570 pounds lighter than the big battery option. And if we compare the total size, they're about the same as the Rely-On batteries, yet smaller than the Battleborn or big battery options. But what about the cost? Well, we can build these for just 30 cents per watt, which means that 33,000 watts only costs us $9,900 in materials. Of course, that does not include our labor to source all these parts, or to manufacture some bits and assemble the batteries. We think each battery will take about 2 days of work to assemble, so that's about 2 weeks for all 6. Still, if we do the work, we can build these batteries for that low price. So these prototypes will cost about $10,000 to build. That's around $8,000 less than the big battery option, $22,000 less than the Battleborns, and $27,000 less than the Rely-On. Even if you add in the labor of, say, $3,000, they're still $13,000, which is the least expensive, and you get a better battery. All right, let's take a look at the safety elements and other nice features in this design. Here's the internal view of the battery. I'll spin it around for you to look at. The battery uses 8 3.6 volt LiFePO4 prismatic cells, which are sandwiched between 2 aluminum plates. These plates are put under compression using 8 springs to keep them around 12 psi while charged or discharged, which is within what the cell manufacturer recommends for low and high compression. There's an HDPE plate attached to the front of the battery, which is used to mount all the systems we added to monitor, cool, and control this battery. Now, let's take a quick look at those electronics. I'll spin the battery around and stop at that HDPE panel. Here you can see where we mounted the internal 200 amp circuit breaker. This can also be used as a switch to cut off the batteries from the external terminals. Next, down below, here is the external cutoff switch, which allows us to turn off this battery without opening the case. Now, we get to the heart of the control systems. This is the JKBMS, which has excellent reviews and a lot of excellent features. For example, it has low temperature cutoff, over and undercharge protection, high and low cutoff settings, maximum charge and discharge amount settings, Bluetooth connectivity to allow easy adjustment of the parameters without opening the case, and a 2 amp active balancing system, which uses capacitors to move energy from the highest charge cell to the lowest. Most BMS units use MOSFETs and just burn off excess power from a high cell, which causes heat and loss of that energy. This system will keep the cells nicely in balance. This is the coulometer with shunt, which will give us an external readout of this battery's state of charge. Again, without having to open the case or check with the Bluetooth app. And here we have the thermostat for the active fan cooling system. The bottom number is the current temperature inside the case, and the top number is the temperature at which the two 120 millimeter low wattage fans will kick on until the internal temperature inside the case cools down a few degrees. Most of the time, the active fan system won't be needed, since there is a passive cooling system with a large heatsink to dissipate internal heat out of the sealed case. Of course, when we're in a cold environment, where the temperatures are getting below zero, that can harm a LiFePO4 cell if it is charged in that situation. The JK BMS will cut off charging if that happens, but we have a thermostat-controlled heating element in the case to keep the cells warm enough so that the JK BMS does not have to cut off charging. The highlighted box is the 48 volt to 12 volt transformer that feeds power to the thermostat and heating element under the battery cells. Next up, we have a pre-charge unit that protects downstream capacitors from a surge of power when the big battery is initially turned on. Over here is the BMS activation circuit, which is used to start up the JK BMS when needed. There are two cutoff switches for the active cooling and heating circuits. These switches are mounted externally so that we can turn off those two systems anytime the batteries will be in storage or when these systems won't be needed. That way, they don't draw energy out of the batteries when we don't want them to be active. So these are the electronics we use to control our batteries. But let's take a look at what's up on top. Remember that we have these cells under compression using springs, which means that as the cells charge and discharge, they will expand and contract slightly. We don't want that movement harming the cell terminals due to hard bus bars. So we're using flexible bus bars, which allow expansion and contraction. Those are the orange bars you see now. While we're here, you can also see the individually fused BMS wires, which, among other things, are used to balance the cells. Okay, let's strip away all the systems we just showed you and take a look at the cell separators we 3D printed. The issue we wanted to solve was that we need to put the cells under compression, but we don't want them pressed against each other with no airflow between them. So we 3D printed these separators that will allow both compression of the cells and airflow between them for cooling. Here are the LiFePO4 cells inserted into the separators. The dark slots between them are where the air can flow up from the bottom to cool the cells. Now let's put this whole thing back together again. All the systems back in and inside the box, and there you have it. What we have now is a 24 volt, 230 amp battery. If we put four of these together, two in series, we get 48 volts and about 460 amps on the main boat. On the tender, we put two of these in series and we end up with 230 amps at 48 volts. In an upcoming video, we will begin building the prototypes of these new lithium batteries for ThermalWorks, and we plan to share that entire build process with all of you. Once the first two batteries are completed, we will take Traveler on a sea trial to test our tender range and speeds using our modified E18 Stealth electric outboard on our 12-foot Inmar 365R AL rib. You can learn more about that boat and the outboard in our last video. Here's that link.
Eventually, the batteries we're prototyping in these videos will be made into a commercial battery for sale. We have no idea how long it will take ThermalWorks to bring these batteries to market. That's up to them, but they have promised to have ours ready for use on SV Lynx and Traveler by the time we set sail on our first circumnavigation voyage.
Remember, our upcoming videos about how we built our prototype batteries are not meant to be instructions on how to build these batteries. We can't assume the liability for that. So we're just showing you the process we use to prototype my designs for ThermalWorks. However, just in case you're interested, we will post a full cost breakdown of the parts we use for these prototypes in our Patron crew pages on the SV Lynx website. I'll post on Patreon when that list is up for patrons to view.
Now, if you do decide to build your own lithium batteries to get this low price, you're doing so at your own risk. These are not how-to videos. We're just showing you how the prototypes were made for ThermalWorks.
Also, Remember that insurance companies don't want to insure boats with DIY batteries on board. So we aren't recommending you build these yourself. Far from it. If you want some of these batteries, we suggest you wait and purchase the commercial versions from ThermoWorks, like we're doing. Yes, they will cost a bit more than the prototypes because, like all companies, ThermoWorks must make their cut on all the work they do to construct these batteries.
So, thanks for watching this episode about lithium batteries and how and why we went the way we did.
If you have any questions about them, feel free to post them in the comments and I will try to answer when possible. Now, as to our shipping woes from South Africa, I promised to tell you about our possible solutions. If the shipping company in South Africa cannot find a ship that will take our cargo soon, we may have to ask Schionning to ship the container without the epoxy on board. That will clear the container to ship, but we would then have to purchase our West System epoxy locally. That will likely cost some extra cash, but it's better than being further delayed, which has its own extra costs.
We should mention that this shipping fiasco is not something that Schionning could avoid. The container was only deemed hazardous by the shipping company at the last moment, right before loading our container. Schionning had our gear loaded, on time, ready to go, but this is still costing us time and money.
Before we go, we'll take a couple of our viewer questions about last week's video. Bill asked, the Torqeedo salesperson told me not to get an electric motor for a high-field 360 because they said that the horsepower to battery weight ratio just wasn't there yet, and so it would either never get on a plane or weigh too much. Do you agree? Well, there's no way that a Torqeedo 1103 or an ePropulsion Spirit 1.0 Evo can get a 12-foot dinghy up on a plane. But the question you should ask is, did you expect it to? The Evo is only for putting us over to a beach and through some light surf so that if the dinghy flips over, nothing dire happens to our propulsion system. The whole reason we are making a convertible tender dinghy is to have a larger electric motor that can put Traveler up on a plane. We use that motor to convert Traveler into our tender for a long distance trip and use the Evo when we want her to be a dinghy to go slow to shore. Jesse Jones asked, did you look at the OC tenders? Well, we absolutely looked at them. I even spoke with the owner of the company several years ago. Back then, he told me that he was working on a larger model, the OC400, which has now come out. It's big enough for our needs, but costs a crazy amount of money, $22,000 US. I didn't call them out by name in the video, but I did mention carbon fiber hull boats, which includes OC tenders. Besides the price, the issue with their design is that it has a very flat bottom. This helps their tender go fast with a smaller outboard, but the trade-off is that in any kind of serious chop, that tender is going to pound like a jackhammer on concrete. Since we plan to go out in many different conditions, sometimes on the open ocean, we won't always be cruising around in a calm anchorage, so we need a tender that can handle any condition. And that's why we went with a deep V rib hull. It's just more versatile. So thanks for the questions. We'll see you all in next week's video. All right, like always, we'd like to end our video by thanking our patrons. We really appreciate them. Over here, we have our newest patrons, and over here, our loyal patron. So thank you again, and thank you all for watching. We really do appreciate you, even if you're not one of our patrons. See you all next week.